Welcome to video 4 from the Standard Library Fixed Objects module. In this video we'll cover the server object from the Standard Library. The server object is a very important object. It's probably the most used object in the Standard Library. It's also very comprehensive. There are lots and lots of features and functionality supported by this standard server object. In this video we'll go through the topics relatively quickly, and we will come back to the server object again and again throughout the course, filling in the details and providing additional examples. So in this video we'll talk about the basic server object. We'll talk about ranking and selection, shift transition, server reliability, secondary resources, the financial modeling using the object, and finally we will talk about the source server sink model. The server object, as we've discussed previously, consists of three stations: the input buffer, the processing station, and the output buffer. An input node where entities enter from the network or from free space, and an output node where entities exit, again, to the network or through free space. And so the server models a standard seize, delay, release model where entities arrive, and if a unit of capacity of the server is available, the entity seizes that unit of capacity, delays for some period of time for processing, releases the unit of capacity, and then departs. Both the input buffer and the output buffer can have specific capacities, so we can either set those to infinity, in which case they are not capacitated, or we can set the capacities to a particular value, which would limit the number of entities in either one of the buffers. If we set the buffer capacities to 0 on the input buffer, then entities don't leave the network, so they wait at the network until they have capacity at the processing station, and then they move directly from the input node into the processing station. Similarly, if the output buffer has capacity 0, then entities will remain at the processing station and will move directly back onto the network. And so in the case where the input buffer capacity is 0, if the processing is at capacity, so if the processing station is busy, then entities will wait on the network and therefore block entrance into the server object. We'll see examples of this type of behavior later on in the course. The server processing can either have a fixed capacity or can operate on a schedule, so a work schedule. So let's jump into Simio and have a quick look at this. If we place a server object here, we can see that we have an initial capacity right here, and this sets the capacity for processing. So the default is 1, which means you can process one entity at a time. If I change that to 2 or 3 or 4, that would dictate how many entities can be simultaneously processed in the server. I can also change the capacity type from fixed to work schedule, which lets me specify a schedule over which the resource is available. So for example, if I wanted to schedule a worker who arrives at 7, works to 11:30, then takes an hour lunch, then comes back at 12:30, I can model that type of behavior with a work schedule. And so we'll see work schedule, an example of work schedules, a little bit later on in the semester. But the fixed capacity, again, has the same number of units of capacity throughout the run. Also, the processing time, when an entity has access to the unit of capacity of the server and goes through the delay for the seize, delay, release process, the processing time can be specified using an expression. So let me make this a little bit bigger so we can actually see. And so we have the processing time specified here as triangular, an observation from the triangular distribution with parameters 0.1, 0.2, 0.3. So we can change that to any expression that we want. We can also control the units of time. Simio, the server object also supports some more comprehensive method for processing type called a task sequence, which we will get into a little bit later in the course. We'll discuss ranking and selection, reliability, and secondary resources in a couple of slides, the next slides. But I wanted to mention that the server also supports many advanced options to control the occurrence of simultaneous events, reservation, multiple process phases, and so on. So as I said earlier, we're just hitting the highlights in this video. We'll do a little example, but throughout the remainder of the course, we'll come back to the server over and over and go through more detail. So the notion of ranking and selection, basically we are ranking entities that are waiting in an input buffer, and then we're selecting the next entity to be processed. Simio ranks entities by FIFO, first in, first out, LIFO, last in, first out, or by a value of any state or expression. So if we jump into Simio again and look at the server, so let's take our server instance here. Here's the ranking rule. So first in, first out is the default. Last in, first out, and then you can have smallest or largest value first. And if you choose smallest or largest value first, then you have to give it a ranking expression to do that selection. To do that ranking with. And so, like in this case, we have an entity with priority 5, and then we have a queue of entities here. And so, if the ranking rule is set to first in, first out, then entity 5 would be the next one to access the server because it's the first one in the queue. If it's set to smallest value first by entity priority, then we would jump over and we would select the entity here with priority 1 because it's smallest value. Entity's largest value first, then of course we would pick entity 6. So unless you choose dynamic, which we will see in just a second, the resource always selects the first member, rank 1 of the queue. And so what's shown here is first in, first out order. If we had another entity like entity priority, the queue would be ranked according to that priority value. And again, the resource always chooses the first member of the queue. So if you choose dynamic, however, dynamic selection looks at all of the queue members before the allocation and picks the best one according to some rule that you provide. So in other words, instead of just taking the first one in rank, it looks at all of the entities in the queue and picks those and picks the one that best meets the criteria. And these rules may be used to either optimize locally or globally. So for example, I might want to minimize setup. I want to look at all of the entities and I want to choose the one that minimizes setup. This would be an example of a local optimization. I might also want to use something like critical ratio, where I have the work remaining divided by the time remaining until that entity is due. And so this would be more of a global optimization because as time progresses, these values change and entities might move around in the ranking of the queue. And so we can do that on the server when we have dynamic selection rule that we see here. Again, we can have largest value first, smallest value first, and then we have a value expression and so on that we want to use to do that dynamic expression. You can see an example of dynamic selection if we go to SymBits and just filter down to dynamic selection. And you can see there is a SymBit that minimizes setup time. And so it uses dynamic selection to minimize setup time when we have sequence-dependent setups. And so Simio provides tremendous flexibility in these dynamic rules. However, if you want something that's not included in the default object, you can always user write or you can create custom rules that are used for the selection process. With off-shift transition, we specify how the server should behave when we're using a work schedule and the server is scheduled to go off shift. So in the example I used earlier, if the server is modeling a person who's going to take a lunch break and the person is in the middle of processing something when that lunch break time happens, what should happen? And this is handled by something called the off-shift rule. And the default off-shift rule says suspend processing. So basically what happens is the processing time just stops and the resource goes off shift, and when the resource comes back on shift, the processing time continues. We can also suspend you also have a second choice of finish work already started. So this would model the situation where you wanted before going to lunch to finish the work that they were working on, that they had already started. And so you can choose either one of these for the basic off shift. If neither one of these general rules implement the behavior you want, you can also use add-on process triggers, which we'll talk about a little bit later in the course, to implement any desired behavior. And so we have, if you look in the add-on process trigger property group, you have on shift and off shift, and this triggers a process to occur when an entity server goes on shift or comes back on shift or goes off shift. We also have an option to select a different secondary resource on a capacity change or a shift change, and we'll talk more about secondary resources in just a second. Server reliability. The reliability logic in the standard server object allows me to model resource failures, so for example machine failures, and there are 4 different types of failures supported. There's calendar time, event count, processing count, and processing time. And so basically what we're doing for any of these is we're specifying either the time for calendar time and processing time, or count based on for the event count or processing count between failures. So this is uptime, and we're also specifying a time to repair, so that would be the downtime. So we're specifying, if we use calendar time, the specific time in the future when the resource will fail. If we're using processing time, we're specifying the number of units of processing time before the failure occurs. If we're using counts, again, it's the number of times a particular event occurs, or the number of times that the resource is used to process. And we can specify all of these values as random variables if we choose. And as with most other behaviors, we can also customize the behavior with add-on processes. And so we see 2 different add-on process triggers, one for when the resource fails, which will execute the process, the specified process when that occurs, and also one when the resource is repaired. Secondary resources represent another important modeling feature of the standard server object, and this allows me to specify additional resources that are required for processing. So for example, if I'm using a server to model a machine, in this case maybe I also need the machinist, so that would be the secondary resource that's required for processing. And the server object has tremendous flexibility in how we handle secondary resources. We have either a specific resource you can specify, or you can select from a list, so you can have a list of alternative resources. You have an optional move to location, so in this case, for example, if I'm modeling the machinist as a worker object, then a move to location would say find where this resource is currently located, and then move that resource to the server object prior to processing. So in this case, the machinist is required for the entire processing time, but I also have other options for resource seizes and releases. So for example, I can seize a resource that's used on entering, before processing, or after processing. So on entering is when it enters the object. Before processing is when it has entered the processing station but hasn't started processing yet. After processing is when it's in the processing station but has completed its processing, and so on. So I can either have secondary resources for the entire time, or I can specify precisely when within the server processing logic those secondary resources are seized and releases. So this provides tremendous flexibility in terms of the use of secondary resources. And the final functionality that we'll discuss in this video with respect to the server object is the support for financials. Also note that all of the objects in the standard library support this type of financial modeling, not just the server object. And what it provides is comprehensive mechanism for activity-based costing. So I can allocate costs based on different phases in processing. I have capital costs, idle costs, busy costs, holding and usage costs, all specified with properties in the financial property group. It also supports different currencies and allows unlimited roll up to higher cost centers. So you can see here that we have the parent cost center here. There's also a nice symbit that demonstrates the use of financials. So again, just go to the support ribbon, go to the symbit solutions, and then filter down using the keyword financials. And finally, in this video, we can return to the source server sync model that we've discussed a couple of times previously. And so we can just take a source, we can take a server, we can take a sync, we can connect those guys up. Let's just use path objects here so that we can see the, oops, I missed it there. So we can now see the entities. Let me go to my second one. There we go. And now we can run. And so now that we have this simple structure and we've talked about many of the features of the server object, I would recommend that you stop the video and go through some experimentation on things like the capacity and the ranking rule, secondary resources, and so on to familiarize yourself with the basic functionality of the server object.